online lecture 7.2, we're going to be focusing on a type of mapping technique that uses interpolation called isorhythmic mapping. These are two-dimensional, but we can also make them three-dimensional maps that depict a three-dimensional, smooth, continuous numerical phenomena or attribute characteristic. What do I mean by that? Three-dimensional, it has what we call a z-value. We think about like a rain gauge. We have three dimensions in which it creates and adds volume. When we think about topography, the surface, of course, it's going to have undulation. And so it's going to have a z-value, and that's the elevation height. What do I mean by smooth and continuous? It's going to essentially spread out across the entire map. We're going to have essentially a smooth surface. Keep in mind, we're going to have data in which it's nearly impossible to have every single point on Earth to be able to measure it. And so essentially what we have is maybe a few stations, a few points where that particular phenomenon is recorded. Then from there we spread out across that surface, we set out a continuous data set, and it's a smooth surface. It's not something which you're going to see big, huge, abrupt changes unless the data set requires it, like a cliff. But for example, I might have my house is 1 acre away from your house. It's not going to be 75 degrees at my house and 52 at your house. We're going to probably have a closer temperature, even though you might not necessarily have the data being recorded at both houses. You understand the basic idea of data and temperatures. Of course, places near each other are going to be much more similar. So you, my neighbor, are going to have a temperature reading quite similar to mine. What I mean by numerical, that's not ordinal. That's not categorical. So remember, ordinal is ranked data, or the other one, categorical or qualitative, just essentially puts things in groups. Here we're going to be using interval and ratio data. So several examples: rainfall and snowfall. Of course, think about a rain gauge or a snowfall gauge, essentially would collect that information at a particular point. So you would know, okay, at my location I had 2 inches of rain. Temperature, same idea. Barometric pressure, although it's kind of like temperature, these are things that are invisible, but we could put them in a particular z-value and add them as a third dimension. So that's what we see often on weather maps. You'll see the surface, of course, that's length and width, but then you'll see added on top of that rainfall. And so it might be the thickness of a particular cloud, how thick it is, or it might be how much rain fell in a particular area. Same idea there with barometric pressure. You can see areas of high pressure, areas of low pressure. Further, think about the Earth's surface, the depth of bedrock. So think about the depth of the surface. Could also be ways in which we could depict essentially those in the particular isorhythmic mapping. So we're not going to be able to core and every single XY coordinate. We're not going to be able to core and find out, okay, this is exactly how much is at this particular X and Y coordinate. Essentially, it'd be impossible. You have no more surface left. You've cored it all. And so the idea there is we take cores at certain points, at certain locations. So then from that, we can then identify the depth of the bedrock. And then further, topography. We'll look at some cool examples of this later on in the semester, in which we can show topography in the third dimension. It's one of the cool ways to visualize data, especially by using things like vertical exaggeration, where you can make the topography a little bit exaggerated, but still nonetheless you can see the cool undulations of a particular surface. So how are these collected? It's very important. This is point data. So what we're doing is we're taking point data and we're essentially creating a grid. We're creating a raster, for those of you who know the whole vector and raster. So we're taking a point data that's vector, that's found at a certain location, in which it also has data attached to it. So it's got its XY coordinates, but then also has temperature. It has the geologic core characters, this particular limestone, sandstone, whatever it might be. And you might already use this if you've gone out in the field and used a GPS. Essentially what it does is it showcases, okay, it shows you your XY coordinates, but it also shows your elevation, how high you are above the surface. And so it essentially records that particular data. So we see surveyors often use this particular same idea, where you take points and then you from that then interpret the surface by creating essentially a raster or a grid that essentially shows the surface based off of those individual points. So we take discrete data, individual points, and turn it into a continuous smooth surface. Finally, oftentimes we don't need to have a legend. We typically can see kind of these some understood things we know, like, red is going to be hot, blue is going to be cold. In terms of in terms of rainfall, we typically also have kind of a similar pattern. Purple might be higher rainfall totals, whereas green might be lighter rainfall totals. Topography, there's a particular pattern which you see kind of green lowland areas, and as you go up in elevation, it gets to more the mustardy and brown colors and yellow, and then eventually get to the top and has white or your very kind of your paler colors. And so those are essentially ways in which we kind of are intuitive. We already know. A lot of the people in geology who look at geological maps, essentially you already know certain colors connotate with certain things. Yeah, you can put that in a legend, but not always is it needed, because your viewer pretty much is it should be intuitive. They should be able to visualize it and not really have to look for a legend to specifically find where high areas or low areas are for that particular attribute, for that particular phenomenon. Now, if they really want to know specific information, then yeah, that's where a legend would be quite useful. But this is the moral of the story: is there we don't need to always think about a legend with this particular mapping technique. There's two kinds of point data. There's true point data. That's essentially data that can be measured. So once again, a rain gauge collects rain data at a specific location. So that's true point data. And there's another kind, it's called conceptual point data. So that's data that's collected over an area or volume, but considered located at points. So for example, we might use a centroid of a census tract to represent all of that particular values within that particular polygon within that census tract. So you might just use a centroid, put a point right in the middle of it, and say, okay, that's where we're going to then show a particular phenomenon. So it's really not, it's a polygon in which they essentially use the center of the tract. So this is where you need to kind of be careful, not to make sure you're thinking about it logically, you're not cheating, let's say. So when you're, in the conceptual points, keep in mind it's kind of as you'll find out, the computer's kind of creating points. It's adding points to your data. So, you got to kind of double check it and make sure everything is good and there's nothing wonking happening. Finally, points where data are collected are what we call control points. This is a key term. So we'll come across this perhaps in an exercise, but the idea here is once again building some terminology. And so once again, we're using points, point data that we then create and generate a continuous surface from. It's a very simple idea here. We have examples of Isoline or isorhythmic maps. And so the one on the left shows average temperature. The one on the right shows average annual precipitation. So very quickly we can see higher precipitation totals down here in southern Indiana. Also there looks like the lake. You can see the lake effect, higher totals there. Our lowest totals are up there in extreme northeast. I'm not going to give the geography lesson here, but the moral of the story is here, all points along the line are the same value. That means all points along this line are 51 degrees. And so then somewhere in between, we're going to be 50.5, 50.75. And so the idea there is you can see in between these particular lines are all values that are in between. So this is essentially, all things that are 50, all things 49, and so forth. Here's another way which we can think about. Once again, we have a 2D surface, and so we can go out there, we can go out with our GPS, and we can go record particular data showing elevation. I can go all over this particular island. I then record the data that then creates these contour lines that we can then kind of visualize. And so 10, 20, 30, 40, and so we have two peaks. And we can see that there in this 3D version. So this is kind of a way to visualize contour lines on a map. Further, this is also a good way to showcase that we typically like to use, when we use these particular lines, we like to show them on a map using the round numbers. So we wouldn't use like 12, 24, 36. Well, they're all 12. No, we typically use nice round numbers. Maybe 5, 10, 15, 20, 10, 20, 30, 40. So this is where once again the cartographer is making decisions here. How many lines do I want? What's my contour interval? So contour interval in this case is 10. 0, 10, 20, so 10 separates each particular line. Do I want to do 5? Do I want to do 15? But typically, like I said, we want to use nice, round, whole, good numbers. Now, this is a density map, a heat map, which I guess is an example of this as well, this whole concept. But this here, what this does is it satisfies what we call the kind of the thumbnail problem. So if you go visit someplace, I like seeing this where they show a thumbnail map. It shows where all the people who have visited this particular restaurant or where this establishment, where they all are from. And so it's really nice because you can see where people are from. But the problem is, typically local areas or areas nearby, they have this kind of this problem where there's so many of these push pins that are put into the board that you can't really tell. And so this helps to take care of this problem because we have on the left crime data, which shows a kind of a pattern. Well, I see yellow dots everywhere, but are there overlapping yellow dots in particular? And that's what's shown on the map on the right, the density or the heat map. And technically, it's not a heat map. If you're a particular visual or graphic person, there is a term called heat map, which is total different thing, but this has become used as the term has been used as calling this as a heat map. But this is just nonetheless showing areas where there's higher density, higher areas of crime happening, which is kind of hidden when we see a map of all this particular crime data shown at once as dots. So here what I've done is I've taken point data and then subsequently have now created a continuous smooth surface, in this case showing isolines, with yellow having higher rates of crime in these particular areas and darker or purple having lower crime rates. And here is the particular soda pop Coke map we'll hear about later. And this is a particular map in which it interviews individuals at the, we're all people, and so it then tracks it to a particular zip code or a county. And then from there has created this continuous smooth surface, so which was originally point data. So all it was is essentially asking a person, what do you call it? This generic term for sweetened carbonated beverage, and then subsequently get a pattern here. So these areas of red are different from the areas of blue, and all that's shown there. But the moral of the story is here how we take point data, individual people who are surveyed, and then from that create a continuous smooth surface. Here another one calling traffic surface, calling a roundabout or traffic circle. So it's kind of only really an Indiana thing. I really didn't know that kind of this whole Midwestern pattern. We call them roundabouts, but in other places surrounding us, they call it traffic circles. Another example of these kind of these particular maps that shows density. This is, in this case, noise, transportation noise map. And so here we see around the airports that surround the city is where we're going to have higher noise levels, noise pollution levels, especially from the source area. And so from once again, Waldo Tobler's first law of geography, everything's related to everything else, but near things are more related than distant things. And of course, nearest the airport, we're going to be then most influenced by having high levels of noise. Here, what I've done is I've collected a bunch of point data. It could be about anything. It could be elevation, temperature, wherever you want it to be. But so I created these points. And then subsequently, I had to think about what I was doing for drawing on this particular map. I had to think about, okay, when I'm drawing this particular 5 line, I had to think about, okay, well, here's the 3 and the 6. I want to definitely put it between the 3 and the 6. Then I got the 4 and the 7. I probably want to put it closer to the 4 than the 7 because 5, of course, is closer to the 4 than it is 7. Same goes for 4 and 8 and so on. So as I'm drawing this line, I'm thinking about the distance. So essentially, I'm interpolating. There's no data here along this line that says this is 5, but I'm saying, well, this is, I can essentially create a conceptual point along this particular line, and so all points along this line are shown as 5. Further, what this does a good job of showing is where we have, let's say, a steep gradient or a steep change. From here, let's say we have 3, up there we have 22. That's quite a bit of change, a relatively short amount of space or close amount of distance between these two particular points. However, you go down here where we have 15 and 20, and so the lines get spread out more when we have, or we'll say, less gradient or less steep of a gradient. So we have a much, hardly any change from this particular value here to this particular value there. Other things this does is shows how you label, and so you never want to kind of tilt these more than 30 degrees, these particular labels. Also, typically we want to put the label, the text, in the same color as our line. It helps with readability. Further, what you typically do is use a mask underneath the text, and you want that mask to be a color that's the same as the surface below it. So you want it to essentially and be easily seen, but you want the mask behind them. So in this case, I have a white base map, and so I put a white mask. If this in this particular area, the surface would say was beige, then I would want to use a beige mask behind this particular label. Fortunately, with computers, they do a lot of the work for us. And there's a few different other ways besides what we see mentioned here. And I'm not going to go into these too much. This is cartography class, maybe in the GIS or upper level GIS course, or maybe the advanced cartography class, if that ever got off the ground. Maybe we would think about going in and trying to explain this a little bit more, the Greek letters. These are the different things, different options that are available to you. First one called triangulation, another one called spline. There's also another version called spline with barriers. There's the inverse distance weight, or the IDW, and there's also kriging. And within these, of course, there's variations and sub methods as well. But once again, the moral of the story is here we have point data, and so here we have individual points. And then what essentially we do is we create from that a continuous surface. And so we know this particular, let's say this point, let's just say, okay, all things within this are 20. 24, okay, 16, 14, 30. And so our known values, our known points are put over here onto the grid. And so essentially we then can from there start to fill in the gaps, fill in the squares, fill in the grid and say, okay, well, if this is 27 and then this is up here 16, that means I know that 22, it's going to be some number in between 16 and 27. And so essentially what you've done is now we've added a point data, conceptual point data. We've added something which it wasn't added. 22 is nowhere on this particular map here. We don't have that data. We don't have a point there. However, from that, we can interpolate. We can guess using good judgment, in this case, a computerized tool, to help help draw or create a continuous surface from our point data. And so here's from ArcGIS Pro, the help tutorials. And so here I go out and I collect my GPS coordinates and I collect a bunch of data. I walk around and I find areas of high elevation, areas of low elevation. I then take that point data and then from there it interpolates and creates a continuous smooth surface based off of that point data that I collected. And so here's an example of ozone. So they go out and they collect a bunch of ozone data at individual points. And then from there say, okay, this point, this particular data, it's going to have a particular numerical value. We're going to use that as our Z value that then creates an interpolator, or it creates a surface in which we have a more in Southern California and in the valley. AQI. So what's the median value? And so it's the median, is just the average, I would say, for a particular year. And this particular data, it's not at every, I don't have monitors. I don't have specifically the monitor locations. What it is essentially I've taken the data that's available for certain counties. It's not available for all counties. So I took the data that's available for certain counties in which each county is given an AQI rating, a median AQI, so median for a particular year. Then what it does is it took that particular data and then puts a centroid, or a point right in the middle. So for Marion County, Hendricks, Boone, Hamilton. And what's kind of nice about Indiana is most of our counties, the county seats, are located right in the center of the particular county. And so oftentimes this is also going to be where people live. But this is, I'm just playing with centroids, and so don't go too crazy with that. So what I just did was I just did two different automatic, if we go back to our different methods, I just did two of them. And so what we have is we have AQI data. So say, for example, Brown has an AQI rating, I'm just going to make it up, of, let's say, 36.9 for that particular year. So its median AQI was 36, average. Whereas down here in Davies County, it was quite low. And of course, Marion. So the moral of the story is with this particular method, it created this interpolated surface. And so we can see that shown as these different colors, these reds and greens. And so this particular area here are lower values, over here lower values, but higher values in the more industrial areas of Marion County, but also the I-69 corridor, but heavily there along the lake, possibly more influenced by Chicagoland. In Chicago than what actually might be happening up here in this particular part of the state. Then I did another one. This is the inverse distance weighted value, so IDW. So they create different maps. Once again, same point data, but creates doing different ways of creating this continuous surface based off those individual point data that are created from the centroids. And our book also shows different methods and how it kind of shows a particular same data set, how it can represent it differently based on the type of method and submethod that you choose. Now I'm going to talk about two different types of mapping techniques that aren't really necessarily isorhythmic, but they're similar in terms of how they might look to the naive map viewer. And so the first one is called the isochromatic mapping technique, and all it is isolines that show distance or time measurements from a particular specific point or origin. There's a few different apps out there that might show this. For this particular one, I use the Travel Time app, and so this is the travel time to the IUPUI Campus Center. So this is travel time. And so what I did was I have the 30 minutes driving, and so here is essentially the isochromatic or the isoline, which is showing the distance that would take you if you're wanting 30 minutes to the origin or point of being the IUPUI campus. You'll see back behind there, in kind of that pink, is same idea, 30 minutes, but this time using public transportation. So what this does is it really shows that in Indianapolis, to ride the public transportation network and only have a 30-minute journey or a 30-minute commute, you need to live close to the IUPUI campus. But it looks like some places are a little bit more connected. It looks like to the west side and the northwest side, a little bit more well connected. But whereas if you look at the entire city, it looks like the driving wise, pretty much everywhere. It looks like the north side a little bit longer, but for the most part, all surrounding the campus, it's pretty much 30 minutes in all directions. Another way to show this, using in this case looks like ordinal data. This is the Nuke Map. So this is what if a nuclear bomb of a certain, looks like the 800 kiloton. So what would happen if a nuclear bomb that was 800 kilotons hit our campus? Who would be influenced? And so then it creates a radius. And so this is the same idea, isochromatic map in which it has a point of origin, our campus, and then from there, in this case, a radius that shows blast damage or distance from that particular point. And so beforehand, we looked at time, time as far as commute, an isoline, so all points along that exterior line would be 30 minutes. In this case, all points inside this circle would be a moderate blast damage.